Hi, welcome to AP Chem Speed Review. On our last unit, Unit 9, we're going to be talking about applying the principles of thermo to various real-world applications. This part of the exam is just under 10% of the average weighting. Here's the big write-up from College Board, but the key takeaway here is that this covers entropy, Gibbs free energy, enthalpy, and galvanic cells or electrochemistry. Now, I've already covered about half of this unit in an expanded Unit 6 when I talked about thermochemistry. So I'm not going to cover entropy or Gibbs or enthalpy. Those have all been covered in the expanded Unit 6. But I am going to talk about electrochemistry. Coupled reactions are two reactions with different thermodynamic favorability. And if we have an unfavorable thermal process, we can still make it happen if we use an external energy source. So it won't happen spontaneously, but we can power it with external energy. So for example, we can use electrical energy to drive an electrolytic cell, which is non-spontaneous, or to recharge a battery. A battery will discharge spontaneously, it will create voltage, electricity, but then to recharge it, we have to add energy. We can use light from the sun, for example, to drive photosynthesis. Again, that is a thermodynamically unfavorable process, but with an external power source, we can make it happen. So, and what it's going to take us to is the idea that we can couple a thermodynamically favorable reaction to an unfavorable reaction and get it to occur because the favorable reaction, the energy released by the favorable reaction, will pay the freight for the energy costs of the unfavorable reaction. So in this case, we're looking at ATP. Creating ATP requires energy, so we have to use the conversion of glucose or something like that to create ATP. But then that ATP, as it breaks down, can power other cellular activities that require energy. Is you can couple a thermodynamically favorable process. So for example, the conversion of glucose, breaking down glucose is an exothermic reaction, creates heat, and that can be used to power up the synthesis of ATP, and that ATP then can power the synthesis of other proteins and stuff in the body. So we couple a thermodynamically favorable process to an unfavorable process to create other things that are thermodynamically unfavorable. Often they'll have a common intermediate if the reaction is coupled, and we can total up Hess's law, right? We can take the total of the individual reactions to get the overall enthalpy, and that as long as the delta G is negative, it will overall be a thermodynamically favorable process. So here is an example where we have an intermediate, and it costs us energy to make this intermediate, but we get energy back when we use that intermediate in the reaction. And as long as the delta G that we get back is greater than the delta G we invest, the overall sum of those two reactions is thermodynamically favorable. Okay, so now let's get to, I think, the most interesting part of Unit 9, and that is electrochemistry. So we're going to talk about galvanic, or sometimes called voltaic cells, and electrolytic cells. A voltaic cell is a spontaneous reaction, and an electrolytic cell is a non-spontaneous reaction. Now what we're going to see is that we can generate electrical energy from chemical reactions. And so we're going to look at the relationship between the physical components of an electrochemical cell and how it operates. So this is going to be a very common picture for us here. And this is two half cells. We have a reaction happening here between the copper and the silver. And what's happening here is that as one of these oxidizes, the other one is going to be reduced, and there will be a flow of electrons from one half cell to another. Now, each component of an electrochemical cell, including the electrodes and the solutions and the salt bridge and a current measuring device. They all play a role in the overall functioning of the cell. And we're going to look at two different kinds of cells, a galvanic cell and an electrolytic cell, and they both have many components in common, but the biggest difference is the galvanic cell spontaneously releases energy and an electrolytic cell consumes energy. This is a spontaneous reaction. This is a non-spontaneous reaction. So we're going to look at the direction of electron flow, the reactions that are occurring in each half cell, changes in the electrode masses, whether we get a gas at the electrode, how the ions flow through the salt bridge, all those things. So this is, again, standard half cell, galvanic cell, voltaic cell situation. And what we have here is we have a reaction going on in this half and a reaction going on in this half. And the reaction going on in this half is the ionization of copper. And so ionization is going to happen here at the anode. And as these copper ions are produced, it's going to release electrons, which are free then to flow through the wire and then be reduced over here. So we have a loss of electrons over here, that's an oxidation reaction, and a gain of electrons over here, that's a reduction reaction. This is a different cell where here the oxidation is happening over here on the zinc side. The zinc here is being oxidized and creating zinc 2+ ions. And as those ions are created, they are being pulled by the copper, and they undergo reduction over here on this on the cathode side. So this is the anode side where oxidation occurs. This is the cathode where reduction occurs. This is called the salt bridge. It connects the two and allows ions to transfer to balance out the charges, because as we create more and more zinc +2 ions, we create an overall positive charge here, and that needs to be balanced out, otherwise the battery will stop working. And likewise, as we reduce more and more of these copper 2 ions, there's going to be a decrease in positive charge. And so we're going to need to bring in some positive ions here to balance out that increased negative charge. And so that's the salt bridge. The salt bridge has inert ions that can flow and balance out the increasing charge on both half cells. Notice here that on the anode side, as zinc metal is being oxidized into zinc 2+ ions, it is losing mass. So that metal is being dissolved ion by ion into solution. Whereas over here on the cathode side, the copper is being reduced and added onto. And so you're going to see on the anode side, the metal is going to dissolve, and on the cathode side, the metal is going to be deposited. So the mass of this will increase and the mass of this electrode decrease. Galvanic cells are thermodynamically favored, whereas electrolytic cells are unfavored. And this is the basic difference between them. Another big difference is that voltaic cells, they occur in two separate half reactions connected by either a porous plate or a salt bridge, whereas an electrolytic cell, it can happen in a single container. The half reactions don't need to be separated. These release electrons. Electrons flow spontaneously when we can use those to do work. Here, this is non-spontaneous, so it absorbs energy, it takes energy to drive this reaction. So we're going to look at visual representations and see where the half reactions are occurring, what direction the electrons or the current is flowing, and so on. For all electrochemical cells, oxidation occurs at the anode. So O-N, so anox and red cat, and reduction occurs at the cathode. So just remember red cat, and you'll always get where reduction occurs at the cathode, and therefore oxidation must occur at the anode. And that's true for both the galvanic cell and the electrolytic cell. All right, let's talk cell potential and free energy. Cell potential is voltage. So we're going to look at a standard cell potential and the half reactions that constitute it. And this is all about the redox reactions that occur within the electrochemical cells. Those reactions are either favored, which gives us a positive voltage, or they are unfavored, which gives us a negative voltage, which means we've got to supply external energy for that unfavorable reaction to proceed. Now let's look at our old friend electronegativity. Remember, this is the pull that any atom has on the electrons around it. Anytime you have two atoms, there is a tug of war as their respective nuclei, which are positively charged, try to attract, they pull against the negatively charged electrons of anything that's around them. So here's a very famous reaction here. We're going to take some zinc metal and we're putting it in a solution of copper sulfate. So this has Cu2+ ions in solution, and we have zinc metal. What happens over time is you begin to have this dark black deposit of copper forming on the zinc, and the blue copper ions begin to disappear as they are deposited on the zinc. So what's going on here? So we have a solution of positively charged Cu2+ ions, and as they come into contact with the zinc, the copper 2+ ions have a stronger electronegative pull on electrons, and so it actually pulls 2 electrons from a neighboring zinc atom to reconstitute itself as a copper metal. And the result is that the zinc, as a neutrally charged metal, now becomes a zinc 2+ ion, and it goes into solution. So the copper becomes deposited against the zinc metal, and the zinc metal goes into solution. And that's because copper has a stronger pull and is able to steal those electrons from the zinc. So that's what's happening here, and that's a very important redox reaction. As we're going to see, copper is gaining 2 electrons, so that is a reduction, and zinc is losing 2 electrons, that's oxidation. And this happens because if we look at electronegativity values, we can see that copper has a stronger electronegativity, a stronger pull on all the electrons around it than does zinc. And now, especially copper as a 2+ ion has even a stronger pull than just regular copper, and so it's going to take the electrons from zinc and grab them for itself. This results in a classic redox reaction. Zinc loses 2 electrons, copper 2+ gains those 2 electrons. And this is another image of copper 2+ coming in here, snagging 2 electrons, displacing zinc. So this is a single displacement reaction, and this is what's happening at the micro level. So this pull of electrons, and in this case, where copper wins this tug of war and is able to pull electrons from the zinc, that happens just in the aqueous solution. But you can imagine forcing that reaction to happen at a greater distance. What if you could have copper on one side stealing electrons from zinc, and it was able to do that through a wire? You could actually use the pull through that wire to do work. That's essentially what's happening with a galvanic cell. So if you separate those 2 reactions by a wire and use something called a salt bridge to allow the ions to balance, then what happens automatically when they touch, you can now force to happen through a wire. And so on this side you have the zinc metal, and these copper 2+ ions are calling for those electrons. They're pulling, and because this wire has electrons in it, it allows that pull to transfer all through the wire to the zinc metal. And so this ionization of the zinc and the reduction of the copper can happen even when they're separated. Like it happens through the wire, and we can actually check and check the voltage or the amount of the pull, electromotive force, or the E cell potential. It's just all those, or voltage. Those are all different ways of saying, ways of measuring this pull that the copper has on the zinc ions. And now it's able to accomplish that pull through a wire, and we can put something in between that to either measure that voltage or actually to take advantage of that voltage to do work. Okay, let's talk electricity. Electricity is essentially the flow of electrical charges from one half cell that is producing electrons to another half cell that is consuming them or reducing them. So one half cell, remember the zinc, was losing the electrons, and the other side, the copper, was pulling them in and reducing the copper. And so that's what electricity is. It's the flow of those electrons through a wire. And it allows, if you put something in between that, it allows something to use that pull to do work, in this case to light a light bulb. So here's how we're going to measure the charge. We're going to call charge, we symbolize that with Q. We know at the subatomic level we have a unit of charge on every electron. Every electron has a negative charge, and that's balanced out by the positive charge of every proton. So the charge on an electron is known as the fundamental charge or the elementary charge. And it's negative for an electron and it's positive for a proton. Millikan, remember Millikan's famous oil drop experiment, he was able to determine the charge on each individual electron. And it turns out to be very, very small, 1.6 times 10 to the negative 19, which is for each electron. So since electrons are so very tiny, you would expect this fundamental charge to be very, very small, and it is very small. We measure it in coulombs, but just it's a very, very small number. So in order to get a lot of charge, a charge that matters in the laboratory or matters in the real world, we need a much bigger unit of electrons. We need to count electrons by great big gobs of them, similar to the way that we count things by moles, right? We use Avogadro's number to get a usable amount of something. So we're going to need a bigger unit to count electrons, and that turns out to be the coulomb. We're going to use something called the coulomb. And a coulomb is 6.2 times 10 to the 18 electrons. It's the combined charge of 6.2 times 10 to the 18 electrons. That would be the negative charge, or if you're counting protons, it would be a positive charge. So it would be basically the same number of protons. So that's what a coulomb is. It's a giant chunk of electrons that gives us a big enough charge to matter. So if you take 6.2 times 10 to the 18 electrons, that's a coulomb of charge. It's the combined charge of that many electrons. Now, why they didn't take a mole is a little bit beyond me, because it would have made things a lot easier. But this number is a big number, but it's not quite as big as a mole. It turns out you need about 100,000 of these coulombs to make a mole of electrons. In fact, you need 94,485 coulombs to make a mole, and that number is known as Faraday's number. So that gives us Faraday's constant, which is 94,485, sometimes rounded to 94,500 coulombs per mole of electrons. So if you have a little under 95,000 coulombs, then you have Avogadro's number, a mole of electrons and a mole of electron charge. Okay, so now we're talking about current. We symbolize that with an I. That can be thought of as the rate of flow of coulombs or electrons through wires. So we can talk about the amount of electrons we have, and then we can talk about how fast they're passing any given point on a wire, for example. So we're going to define the current passing through that arbitrary point as amps. So an amp is when you have 1 coulomb of electronic charge flowing for 1 second. So an amp we define as coulombs per second. Again, a coulomb is this, 10 to the 18th electrons of charge passing any given point in 1 second. So just like if you wanted to find the amount of fluid that was coming out of your faucet, right, you would take the rate of flow. You'd say, hey, my faucet is putting out 5 gallons a minute. And so if I let it run for a minute, I'm going to have 5 gallons of fluid. Right? Well, by analogy, we can calculate charge the same way. We can say, hey, if I have a certain amount of coulombs per second passing through this point, and I let that happen for 10 seconds, then I'm going to have 10 coulombs of charge at the end of that. So this is the total charge, the total electrons transferred. This is the rate at which they're flowing, and this is how long we let them flow. And so this is our very simple formula. Q, that is charge in coulombs, equals our amperes, our rate of flow, and our time that we let that flow. We're going to talk now about potential difference, which we symbolize with a V. It stands for volts. And potential difference is short for potential energy difference. And it's going to be the amount of pull between the two half cells. Essentially, the amount of pull that the copper is going to exert on the zinc half cell. The total pull, the electronegative pull that it's exerting to try to get those electrons to cross through that wire. Because the copper is pulling on that and it says, come over here to our side, join the dark side. The voltage is simply going to be how much work could you do bringing a coulomb of electrons from the zinc side to the copper side. And that is voltage. So we define a volt as the work done by bringing over 1 coulomb of electrons. Think of it this way. It might be easier to think of it in terms of rocks first, and then we'll talk about voltage. Right? But imagine if you had a rock at a higher potential. Let's say this rock is up here at the top of a cliff. It's 100 feet high. That rock would have a certain amount of potential energy because it's up high. Right? We would say, it's that potential energy is actually equal to the mass times gravity times the height. So the work that it can do is equal to its height above the ground. And so if you could take this rock and roll it downhill, and as that rock fell down, that height difference, it could do work. All right. Well, that's similar to what's happening with charge, because what we have here is we have a higher charge and a lower charge. And what's happening here is charge, just like the rock, it wants to go from high to low. It wants to fall down and get to this lower point. And you could do work by letting it fall, by letting it jump. So here, this is a gravity jump. Here, this is an electro. So down here, for example, this would be the copper pulling on these electrons. And if you just let them fall, you could actually do work as these electrons go from the zinc side down to the more energetically favorable copper side. So that's what a volt is. It is the amount of work you could do if you allow a coulomb of electrons to fall from a higher place to a lower place, to jump from zinc to where copper is pulling them. So the work is what you can do when you allow that drop. So we call that pulling force the cell potential, E cell, or we also call it the electromotive force, or the EMF, and we measure it in volts, right? And a volt will do a joule of work per coulomb, right? That's 6 times 10 to the 18 electrons per coulomb of charge that's pulled over or transferred from the higher to the lower voltage, or the higher potential to the lower potential. So we define a volt as 1 joule of work per coulomb of charge transferred. And the units there will be joules per coulomb. Just think of voltage as the electromotive force that is pulling the electrons across the wire. Sometimes people think of it as a push, but it's really a pull. It's the reduction side is pulling the electrons from the oxidation side. Okay, so if a volt means how much work you can do when you pull so many coulombs across the gap, then the more volts you have, right, the more work you can do per coulomb. So think of voltage kind of like pressure in a water pipe, right? So the higher the water pressure, the more you can push the water through. And so more voltage means more pulling pressure if you're looking at it from the reduction side, or more pushing pressure if you're looking at it from the oxidation side. But it just means it's how much it wants those electrons to cross. And the more voltage, the bigger the voltage difference between those, the more work you can do when you make them flow. So we calculate standard cell potential by identifying the oxidation half reaction and the reduction half reaction and their respective standard reduction potentials. And we do this with a table of reduction potentials. And as we're going to see, based on electronegativity and our activity series that we've seen before, some electrons really, really want electrons. They really, really want to grab electrons and be reduced. Okay, and some atoms are happy to give up their electrons. They want to be oxidized. So these are strong. These want to be reduced, and so they are very good at grabbing electrons from other places. So we say something that is strongly reduced is also a good oxidizing agent because it's being reduced because it's causing the loss of electrons from someplace else. It's like we would say a thief is very, very good at causing property loss, and it is very, very good at gaining that property for itself. So these strong reducers are also great oxidizers. They love to oxidize or cause these other atoms to lose electrons, which they themselves can take to reduce. In any case, we use these standard reduction potentials to figure out what's happening in each half reaction. And what we're going to see is that the higher the reduction potential, the higher the voltage, the stronger the pull on electrons, the higher the voltage number, that means the stronger these will be in grabbing electrons. And if you pair them up with something else that's less strong, it will cause the less strong voltage to become the losers. If we take F2 fluorine and we pair it with, say, gold, okay, well, this is much a stronger reducer. It's going to make the gold turn into the oxidizer, and so it will flip this reaction from a reduction reaction into an oxidation reaction. So the cell potential is simply going to be the difference between the two reduction potentials, the two half-cell reactions. So if we go back here to this one, what's the cell voltage that we could make if we had a battery created out of a fluorine half cell and a gold half cell? Well, this would be positive 287, and then we would subtract this because this is now an oxidation reaction. So 2.87 minus 1.50 would give us something like, what, 1.37. So the overall voltage would be the difference between those two reduction potentials. And that's what this formula would give us. E cell is the E reduction minus the E cell of oxidation, which is the reduction flipped. We can calculate this, this reaction we keep talking about, by looking at the standard cell potential, and we can say, hey, the E cell for this entire battery will be the sum of these two half cells. And what we see is that copper is pulling on these electrons with this kind of pull or voltage, and zinc is only pulling on them this much. So this zinc is going to be reversed, and this is going to become the oxidation. So we're going to calculate the cell, we're going to take the E of the reduction, okay, minus the E of the reduction of the part that gets oxidized, and that changes the sign, and when you add that together, you end up with a 1.1 voltage. Now it's important to remember that voltage is what's known as an intensive property. So it does not depend on the amount of matter present. Other intensive properties that we've talked about are melting point, boiling point, density. Okay, but those don't matter. Temperature, right? It doesn't matter how much you have. The boiling point of water is always 100 degrees Celsius. Right? The density of water is always whether you have a little or a lot. And so this ability to conduct electricity is likewise an intensive property. It's not going to matter how much of a thing we have. Now, this is different from extensive properties, which do matter on the amount of material you have. Right? If you combust a larger amount of propane, for example, you're going to release more energy. Right? So extensive properties, you know, we use those when we're doing energy calculations, when we're calculating entropy, when we're calculating Gibbs free energy, okay, mass or length or volume or anything like that. These are extensive properties. But intensive properties, they are things like density or pressure or specific heat capacity, temperature. They're not going to depend. And voltage is one of those things that doesn't depend on the amount of something. So it's not going to change. If you have 1 mole or 2 moles or 3 moles, we're not going to use the stoichiometry to multiply voltage. The voltage is going to be the same no matter how much of a thing we're reacting. So it's important to remember that. Unlike all the other, delta H and delta S and delta G, those matter. And the number of moles we're dealing with matters, but not so with voltage. Okay. So when we talk about standard Gibbs free energy, we have to remember that it is proportional to the negative of the cell potential. And so we're going to see that they have an opposite sign. So a cell with a positive E cell, a positive voltage, that is going to be a thermochemically favorable reaction. And a cell with a negative voltage is going to be an unfavored reaction. This is the formula that relates voltage to Gibbs free energy. And as you're going to see, they have opposite signs. So when E is positive, when we take the negative of that, so when E is positive, we'll get a negative delta G. And when E is negative, we'll get a positive delta G. Now let's look at cell potential under non-standard conditions. All right, so we're going to show the deviations from standard cell conditions and changes in the cell potential. What are standard conditions? Well, standard conditions are when the concentration of the anode, the solution at the anode, and the concentration of the solution at the cathode are both 1 molar. If that is not the case, then we are under non-standard conditions, and the cell potential will vary depending on the concentrations of the solutions at the anode and the cathode. Remember, cell potential is the driving force, or the pull towards equilibrium. And the farther the reaction is from equilibrium, the greater the pull. The opposite is also true. The closer the reaction is to equilibrium, the less the magnitude, the less the cell potential and the resulting voltage. Now, we do not use Le Chatelier's principle to electrochemical systems because Le Chatelier only applies to systems that are in equilibrium. These are not yet in equilibrium. At equilibrium, the voltage of a cell is 0. So we're talking about, that's a dead battery. So we're talking about something that's tending towards equilibrium, but it's not there yet. So we don't use Le Chatelier's principles to make the arguments. What we're going to do is look at our Q value. And Q is our reaction quotient. And we're going to see that the standard cell potential corresponds to standard conditions where Q equals 1, where the molarity of the products to the reactants is a 1-to-1 ratio. And as the system approaches equilibrium, the magnitude of the cell potential is going to decrease. And it will finally reach 0 at equilibrium. So when Q gets to K, that cell potential is going to have declined all the way to 0. So that means that at 1, it's a long ways from equilibrium. But as it gets closer and closer to equilibrium, its cell potential, its voltage, is going to decline until it gets to 0. So deviations that take us closer to equilibrium will decrease the voltage. Deviations that take us further from equilibrium will increase the voltage, the cell potential relative to the standard cell potential. And that's what this is, standard cell potential. So if we go closer to equilibrium, we're going to decrease voltage compared to our standard voltage. And this is the basis of what's known as a concentration cell. You can actually have 2 half cells with the same ions in there. So you can make a concentration cell both out of copper sulfate, Cu2+, where one is a very, very low concentration and one is a very, very high concentration. And that concentration difference will cause a spontaneous electron flow. So here is a concentration cell. It has the same electrodes in each half cell, but the concentration of the electrolytes is going to be different. So here on the anode side, we're going to have a very, very low concentration of Cu2. And here we're going to have a much, much relative. So this is going to be 1/100th of the concentration here. And that concentration difference will cause these electrons to want to flow from the area of low concentration to high concentration, and there will be a positive voltage associated with that. So we can qualitatively understand the effects of concentration on cell potential using the Nernst equation. Now, you're not going to have to use the Nernst equation for a quantitative purpose, but you will be asked to make qualitative analyses. And basically what you're going to do is say E cell at any given time, if it's not standard conditions, is going to be our standard voltage. So you have to be able to calculate the standard voltage. And then we're going to adjust it by this fudge factor. And essentially what's going to happen here is if Q is at normal conditions, 1-to-1, then the natural log of 1 is 0, and then this whole term disappears. So when Q is 1, our cell potential is going to be our standard cell potential minus 0, so it's going to be standard cell potential. That's our reference. So what happens then if Q gets bigger or smaller? That's the key. If this number becomes a fraction, so let's say the products are very, very low, and that's the concentration of the anode, and the concentration of the cathode is very, very high, Q is going to become a fraction, and the natural log of a fraction is going to be a negative number. And so when we subtract a negative number, it's going to add to the voltage of the standard cell. So it's going to be the standard voltage plus something a bit more if Q is a fraction. If, on the other hand, Q is not a fraction but a whole number, say 4 to 1 or something, then the natural log of a positive number, a number bigger than 1, is going to be a positive number, in which case we're going to be subtracting a positive number, so we're going to be reducing our cell potential from our standard cell potential. So basically, if Q is less than 1, we're going to increase the voltage from the standard voltage. If Q is greater than 1, we're going to be reducing the voltage from the standard voltage. All right, here's the Nernst equation in all of its mathematical glory, but what you really need to be able to do is simply analyze Q. Remember, Q is the concentration of products over reactants. If Q is greater than 1, that gives us a positive number, so we're subtracting a positive number, right? And that's going to reduce our E cell from our standard voltage. Contrary-wise, if Q is less than 1, it's going to make natural log of Q a negative number, and subtracting a negative is going to be the same as adding a positive. It's going to add voltage to our standard voltage. So our resulting voltage is going to be more than our standard voltage. Let's talk about electrolysis and this guy named Faraday. We're going to be looking at the charge flow based on changes in the amounts of reactants in an electrochemical cell. In this case, we're talking about a non-spontaneous cell. Electrolysis is defined as a process of decomposing ionic compounds into their elements by passing a direct current through the compound while it's in a fluid form. So that can be an aqueous solution, or it can be where you have an ionic compound that's melted at a very high temperature. So here are the basic differences between a voltaic or galvanic cell and an electrolytic cell. Right here, we're converting we're using a chemical conversion to create electrical energy. And this is a spontaneous reaction. Okay, so our zinc is giving up its electrons. The copper is pulling them through the wire to cause reduction at the cathode and oxidation at the anode. And here the electrons are going to flow from the anode to the cathode in a spontaneous reaction. So that's a voltaic cell. An electrolytic cell, we're going to convert electrical energy to chemical energy. And it's non-spontaneous. This won't happen unless it consumes energy. And so we're going to force electrons from the anode to the cathode. So notice, oxidation still happens at the anode, reduction still happens at the cathode, but it's going against the spontaneous direction. And so we're having to apply energy to pull those electrons that don't want to, they want to reduce, but we're going to pull them, oxidize them, and deposit them over here on the cathode side. Another big difference that you'll see is whereas voltaic cells happen in two cells with a porous either disk or salt bridge between them, electrolysis can happen in the same container. The half cell reactions don't need to be separated. And so here you have the electrolysis of sodium chloride, salt. And what's happening here is that the sodium ions are being reduced over here at the cathode. The electrons are being pumped in here to reduce the sodium, and those electrons are being pulled away from the chlorine. So the chlorine ions are being pulled away by the battery and shoved over here to the cathode, where it reduces the sodium to sodium metal, and this oxidation, this loss of electrons from the chlorine, it releases chlorine gas over here at the anode. And so this is a way of forming pure elements from ionic compounds. And this way you can get pure sodium metal and pure chlorine gas from salt water. Now we can use what's known as Faraday's laws to determine the stoichiometry of the redox reaction that happens in an electrochemical cell. And we're going to track the following things. We're going to look at the number of electrons transferred. We keep track of that in coulombs, remember. Every coulomb is about 6 times 10 to the 18th electrons. We're going to keep track of the mass of the material deposited on or removed from an electrode. We're going to keep track of the current, that's the rate, and the time, and then the charge of the ionic species. Because sometimes if it's a +1 ion, then only one electron is being transferred in the reaction. But if it's, say, aluminum, which forms a +3 ion, then you have 3 electrons being involved in that reduction. So here's the equation. We've already mentioned it before. Q equals IT. And so this is the charge in coulombs. That's the number of electrons that are being transferred. And that's going to depend on the rate at which they're being transferred. So that's the current, the coulombs per second. So that's amps. So 10 amps is 10 coulombs per second. And then we keep track of time in seconds. Another thing we can use electrolysis for, not just the creation of elements, but we can do what's called electroplating. And that's what we saw when we had copper forming on that zinc metal. That copper being reduced was forming a thin layer of copper on top of the zinc metal. And that is characteristic of electroplating. And typically it takes energy to do that. So here would be an example of, we're taking nickel, the metal nickel, and we're going to electroplate it. We're going to make a thin layer on this iron spoon. And again, it's thermodynamically unfavorable, so we've got to force it to happen. And so we're going to force nickel to become ions that will then reduce over here on the iron, and will form a thin layer. And the longer we let it electroplate, the thicker that plating, that layer of nickel will be. So Faraday's law basically says, hey, we can figure all that out. We can figure out the mass that's going to be, either created at a cathode, if you're making elements, or if you're doing some electroplating, how much is it going to be? So the key is 3 basic steps. The first thing you're going to do is you're going to find the total number of electrons transferred. That's coulombs, right? So that's our formula. Q, that's coulombs transferred, equals our amps, our coulombs per second, times however many seconds. Once we have the coulombs, we're going to find the number of moles that we have. Remember, coulombs are number of electrons, and each coulomb is about 1/100,000th of a mole. So now we need to find the number of moles. Well, then we're just going to take our total number of coulombs and divide it by Faraday's constant, which is 96,500. And that will tell us the number of moles of electrons transferred. And then once we have that, we're going to figure out how many electrons per half reaction we're talking about. So in some reactions we need, so for example, if we're reducing aluminum, Al3 plus to aluminum, we need 3 moles of electrons per every mole of aluminum that is reduced. So we can use these formulas. So IT, if we divide that by the number of Faradays, so our total coulombs, that's what IT gives us, coulombs, divided by Faradays gives us moles. And if we divide that by the number of moles of electrons transferred, so in the case of Al3 plus, 3 mole, we would take 3 moles of electrons to produce 1 mole of product. But if we were doing something else, that only required 1 mole, then we put that. So whatever number of moles is required in a half reaction, that's what we're going to put down here. And this formula will give us the moles of product that we produce in our electrolysis. And if we want to then convert that to grams of product, then we'll take this formula here and multiply it by the molar mass of our product to get the grams that is produced. Okay, so just a quick review. The total electron charge, the total number of electrons transferred in coulombs is I times T. If we want to get the moles of electrons, we're going to take IT divided by Faraday's constant. If we want to get the moles produced by those moles of electrons, we're then going to divide that formula by the number of electrons transferred per reaction, per half reaction. And then if we want to get the grams produced, we're going to take this formula and multiply it by the molar mass. So key concepts for this whole thing, and we're going to do a super quick review. Entropy is an increase in dispersion of either matter or energy. So if energy goes up, or if moles goes up, then entropy goes up. If temperature goes up, if volume goes up, entropy, the measure of dispersion or disorder, goes up. We track entropy. We track the entropy of a reaction as the sum of the products, that's our final situation, minus the sum of our reactants, that's our initial situation. It's always final minus initial, whether it's delta S, delta H, delta G, doesn't matter. Gibbs free energy tracks the favorability of a reaction. And so when delta G is less than 0, if it's a negative number, that means there's energy that's being freed up to do work. Just like a negative delta H means there's heat energy that has been freed up that can do something, can do work. So a negative delta G means it is a favorable, spontaneous reaction, thermodynamically favorable reaction. It might not be spontaneous, as we'll see, because it might be under kinetic control, but from a thermodynamic point of view, it is favorable. Okay, again, we track delta G, same way. Final situation minus initial situation. And we can relate delta G to delta H and delta S entropy with this equation, delta G equals delta H minus T delta S. And we can keep track of the various ways. There's a chart we can put together to track, when these are both positive or both negative or one of each. What the universe wants exothermic reactions that release heat, and it wants entropy to increase. So if you give the universe both of these things, they will then the reactions will be favorable in all conditions. If you give the universe neither of these things, if you have a positive delta H and a negative delta S, you're talking about an endothermic reaction. It requires heat, and you're not increasing dispersion, you're decreasing dispersion. Well, the universe wants neither of those things, and so if that's your case, then that will be unfavorable in all conditions. So remember, if something is thermodynamically favorable, but you still don't see a measurable reaction taking place, then it is reasonable to conclude that reaction must therefore be under kinetic control, must have a very high activation energy or something, which is why it's not happening spontaneously. It's thermodynamically favorable, but the kinetic activation energy is what's keeping it from happening. When delta G is less than 0, that's thermodynamically favorable, then K will be greater than 1, which means the reaction will favor products. Delta G is greater than 0, which means non-spontaneous, then K, the K value will be less than 1, which means the reaction will favor reactants. We can use external energy to drive unfavorable reactions, and we can couple favorable with unfavorable reactions to get an overall favorable net result. We looked at the difference between galvanic, spontaneous versus electrolytic, non-spontaneous cells. We keep track of where oxidation happens, that's at the anode, and where reduction happens, that's at the cathode. We can look at the voltage of the entire cell, which is the sum of the two half cells. Our standard cell potential assumes that Q is 1 when we have 1 molar solutions of both products and reactants. If Q is greater than 1, it means we have more products, which means our Nernst equation is going to give us a positive value, and when we subtract that, it's going to reduce our cell potential from its standard value. Q minus 1 is going to increase the cell potential from its standard value. When Q goes all the way to K, it is at equilibrium, the reaction is at equilibrium, and there will be no more transfer of electrons, and therefore no pull, no voltage. If concentration cells, we can take advantage of that and create a difference based on a wide difference between reactants and products. That creates small voltage batteries. And then our electrolysis formulas, Q equals IT, and then you take that number and you can divide it by Faraday's constant to get moles, and the moles of the reaction to give you the moles of product. To get it in grams, you just multiply all of this times molar mass. All right, that's it. Thank you for your time.